Dear students, a warm welcome to massive open online courses in chemistry on SWAYAM. I am Dr. Amrita Anand. In the previous module, you have learnt about the catalysis, the types of catalysts, mechanism of catalysis and their applications which play an important role in surface chemistry. After going through this module, you would be able to explain the nature of colloidal state, to classify colloids on the basis of physical state and nature of interaction between dispersed phase and dispersion medium, to describe methods of preparation and purification of colloids, to understand the mechanism of micelle formation, to know how the soaps clean our clothing. Let me first introduce the nature of colloids. Colloid form is intermediate between a true solution and a suspension. Owing to their size, the colloids have unique properties which make them highly adaptable to specific uses and functions and find special applications in industry as well as in life form. Cosmetics, paints, pharmaceuticals, ceramics, food, plastics and rubber and biological processes are some of the most significant applications of colloids. In this module, we will be discussing about colloids in terms of their nature, classification, preparation and purification. We will also discuss the mechanism of micelle formation and cleaning action of soaps. We can begin with an activity to identify colloids. This you can easily do at home also. Take 3 glasses of water and add salt, clay and sand to them and stir. Identify the solution, suspension and colloid. We have learnt in earlier modules that solutions are homogeneous systems. We also know that sand in water when stirred gives a suspension which slowly settles down with time. Between the two extremes of suspensions and solutions, we come across a large group of systems called colloidal dispersions or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed called dispersed phase as very fine particles in another substance called dispersion medium. Study of colloids began towards the later part of 19th century. Substances such as sodium chloride or sugar which formed solutions that could pass through parchment membrane or a filter easily were called as crystalloids, whereas substances such as starch in solution could not pass through membrane or filter and were referred to as colloids. However, subsequently it was observed that even sodium chloride behaved as colloid in benzene. A detailed investigation revealed that a substrate behaves as a crystalloid or colloid depending upon its particle size. The essential difference between a solution and a colloid is that of particle size. While in solution the constituent particles or ions are small molecules, in a colloid the dispersed phase may consist of particles of a single macromolecule such as protein or synthetic polymer or an aggregate of many atoms, ions or molecules. Colloidal particles are larger than simple molecules, but small enough to remain suspended. The range of diameters is between 1 and 1000 nanometer, that is 10 power minus 9 to 10 power minus 6 meters. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 centimeter side. It has a total surface area of 6 centimeter square. If it were divided equally into 10 raised to power 12 cubes, each would be of a size of colloidal particles and have a total surface area of 60,000 centimeter square or 6 meter square. This enormous surface area leads to some special properties of colloids to be discussed later in this module. It is important to bear in mind that a colloid is not a mere substance, but it is the state of the substance which depends upon its particle size. Classification of colloids. Colloids are classified on the basis of the following criteria. Number 1, physical state of dispersed phase and dispersion medium. Number 2, Nature of interaction between dispersed phase and dispersion medium. Number 3, type of particles of the dispersed phase. We will study one by one in detail. Number 1, classification based on physical state of dispersed phase and dispersion medium depending upon whether the dispersed phase and the dispersion medium are solids, liquids or gases. Depending upon that, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. The examples of the various types of colloids along with the typical names are listed in the table. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in a liquid. Fire-fighting foams are also colloidal systems. Most biological fluids are aqueous salts, solids dispersed in water. Within a typical cell, proteins and nucleic acids are colloidal sized particles dispersed in aqueous solution of ions and small molecules. Out of the various types of colloids given in the table, the most common are salts, that is solids in liquids, gels, that is liquids in solids, and emulsion, that is liquids in liquids. However, in the present module, we will take up the discussion of the salts and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the salt is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called alkosol. If it is benzene, then the salt is called benzosol. If air is the dispersion medium, the salt is called aerosol. Number 2, classification based on the nature of interaction between dispersed phase and dispersion medium. Depending upon the nature of interaction between the dispersed phase and the dispersion medium, colloidal salts are divided into 2 categories, namely lyophilic, that is solvent attracting, and lyophobic, that is solvent repelling. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. Lyophilic colloids. The word lyophilic means liquid loving. Colloidal salts directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid as the dispersion medium are called lyophilic salts. An important characteristic of these salts is that if the dispersion medium is separated from the dispersed phase, say by evaporation, the salt can be reconstituted by simply remixing with the dispersion medium. That is why these salts are also called reversible salts. Furthermore, these salts are quite stable and cannot be easily coagulated, as we are going to discuss later. Lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, their sulfides, etc., when simply mixed with the dispersion medium, do not form the colloidal salt. The colloidal salts can be prepared only by special methods. Such salts are called lyophobic salts. These salts are readily precipitated or coagulated on the addition of small amounts of electrolytes or by heating or by shaking, and hence they are not stable. Further, once precipitated, they do not give back the colloidal salt by simple addition of the dispersion medium. Hence, these salts are also called irreversible salts. Lyophobic salts need stabilizing agents for their preservation. Number 3, depending upon the type of the particles of the dispersed phase, colloids are classified as multimolecular, macromolecular and associated colloids. Multimolecular colloids. On dissolution, a large number of atoms or smaller molecules of substance of diameter less than 1 nanometer aggregate together to form species having size in the colloidal range, diameter greater than 1 nanometer. The species thus formed are called multimolecular colloids. For example, a gold salt may contain particles of various sizes having many gold atoms. Sulfur salt consists of particles containing 1,000 or more S8 sulfur molecules. Coming to macromolecular colloids, the macromolecules are usually polymers with high molecular masses. Macromolecules in suitable solvents form particles of size in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solution in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins and enzymes. And those of man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. Number 3. Associated colloids, which are also known as micelles. There are some substances which at low concentrations behave as normal strong electrolytes, but at high concentrations exhibit colloidal behavior due to the formation of aggregates. The aggregated particles thus formed are called micelles. These are also known as associated colloids. The formation of micelles takes place only above a particular temperature called Kraft temperature, which is designated as Tk, and above a particular concentration called critical micelle concentration, and it is abbreviated as CMC. On dilution, these colloids revert back to true solutions. Surface active agents such as soaps and synthetic detergents belong to this class. For soaps, the CMC is in the range 10 power minus 4 to 10 power minus 3 mole per liter. These colloids have both liophobic and liofilic parts. Micelles may contain as many as 100 molecules or more. Mechanism of micelle formation. Let us take the example of soap solutions. Soap is sodium or potassium salt of higher fatty acid and may be represented as RCOO minus Na plus. For example, sodium stearate, which has the formula of CH3CH216 COO minus Na plus, and this is a major component of many bar soaps. Here R is equal to CH3CH216 group. When dissolved in water, it dissociates into RCOO minus and Na plus ions. The RCOO minus ions, however, consists of two parts: a long hydrocarbon chain, or also called non-polar tail, which is a hydrophobic, water repelling, and a polar group COO minus, also called polar ionic head, which is hydrophilic. The RCOO minus ions are therefore present on the surface with their carboxylate in water, and the hydrocarbon chains staying away from it and remain on the surface. But at critical micelle concentration, the anions are pulled into the bulk of the solution and aggregate to form a spherical shape with their hydrocarbon chains pointing towards the center of the sphere and the carboxylate part remaining outward on the surface of the sphere. An aggregate thus formed is known as ionic micelle. These micelles may contain as many as 100 such ions as shown in figure. Arrangement of stearate ions on the surface of water at low concentrations of soap and the arrangement of stearate ions inside the bulk of water ionic micelle at critical micelle concentration of soap are explicitly explained in the diagram. Similarly, in the case of detergents, for example, sodium lauryl sulphate, the polar group is SO4 minus along with the long hydrocarbon chain. Hence, the mechanism of micelle formation here also is the same as that of soaps. Cleansing action of soaps can be discussed here. It has been mentioned earlier that a micelle consists of a hydrophobic hydrocarbon like central core. The cleansing action of soap is due to the fact that soap molecules form micelle around the oil droplet in such a way that hydrophobic part of the stearate ions is in the oil droplet and hydrophilic part projects out of the grease droplets like the bristles. Since the polar groups can interact with water, the oil droplet surrounded by stearate ions is now pulled in water and removed from the dirty surface. Thus, soap helps in emulsification and washing away of oils and fats. The negatively charged sheath around the globules prevents them from coming together and forming aggregates. Preparation of colloids. Salts of lyophilic and lyophobic colloids are prepared differently. In lyophilic colloids, owing to strong affinity between the particles of dispersed phase and dispersion medium, by merely mixing and shaking the dispersed phase and the dispersion medium together, they form the colloids. Gum, egg albumin, gelatin and starch are substances that form lyophilic colloids with water as dispersion medium. Lyophobic colloids are prepared by two methods as described. Number 1, condensation methods, and number 2, dispersion methods. In the condensation methods, colloidal size particles are formed by inducing the small atoms or molecules to aggregate together. This is done by using both chemical and physical methods. In chemical methods, colloidal solutions can be prepared by chemical reactions leading to formation of molecules by double decomposition, oxidation, reduction or hydrolysis. These molecules then aggregate, leading to formation of salts. Now, let us discuss the physical methods. Number 1, exchange of solvent method. For substances like phosphorus and sulfur, their colloidal solutions are prepared by this method. They dissolve in alcohol, but insoluble in water. Colloidal salts, milky salts of these substances are prepared by pouring their alcoholic solution into large quantity of water. Number 2, excessive cooling method. A colloidal solution of ice in chloroform or ether is prepared by freezing a solution of water in the solvent. Molecules of water that cannot be held in solution separate out and combine to form particles of colloidal size. The second method is called dispersion method. In dispersion methods, the large particles of a substance are broken into small particles of colloidal size in a dispersion medium. Suitable stabilizers are used to stabilize these salts. Various dispersion methods are detailed below. Number 1, mechanical dispersion. Number 2, electrical disintegration or Briggs arc method, and number 3, peptization. Mechanical dispersion. Colloidal solutions of inks, paints and varnishes are prepared by this method. The large sized substances of suspension are broken down to colloidal size by grinding it in a colloidal mill or ball mill or ultrasonic disintegrator. In the figure, you can see the typical depiction of a colloidal mill. Electrical dispersion or electrical disintegration, or this is also known as Briggs arc method. This process involves dispersion as well as condensation. Colloidal salts of metals such as gold, silver, platinum, etc. can be prepared by this method. In this method, electric arc is struck between electrodes of the metal immersed in the dispersion medium. You can refer the figure for the explicit explanation. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. So, Briggs arc method is clearly depicted in the figure. Peptization. Peptization may be defined as the process of converting a precipitate into colloidal salt by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. This method is applied generally to convert a freshly prepared precipitate into a colloidal sol. During peptization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on the precipitate. These repel each other and ultimately lead to the breakup of the precipitate into smaller particles of the size of a colloid. When a small quantity of ferric chloride, that is a peptizing agent, in this instance is added to freshly prepared ferric hydroxide particles, ferric hydroxide particles absorb Fe3 plus ions and form dark reddish brown colored ferric hydroxide salt. Purification of colloidal solutions. Colloidal solutions, when prepared as described by any one of the above methods, generally contain excessive amount of electrolytes and some other soluble impurities. While in presence of traces of electrolyte is essential for the stability of the colloidal solution, a larger quantities coagulate. It is therefore necessary to reduce the concentration of these soluble impurities to requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution is carried out by the following methods. Number 1, dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles, that is ions or smaller molecules, in a true solution can pass through animal membrane, that is animal bladder or parchment paper or cellophane sheet, but not the colloidal particles. The membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing, which is clearly shown in the figure. The molecules and the ions diffuse through the membrane into the water and pure colloidal solution is left behind. Dialysis plays an important role in purification of blood of patients with kidney failure. The kidneys carry out critical functions of purification of blood by removing waste products like urea and excess electrolytes from the blood. When the kidneys fail to function partially or totally, the purification of blood has to be carried out externally, that is outside the human body, with the help of artificial kidney machine, which works on dialysis principle. The blood is passed through the machine where the harmful products are filtered out. Electrodialysis. Ordinarily, the process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substances in the impure colloidal solutions are electrolytes. The process is then named electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment as shown in the figure. The ions present in the colloidal solution migrate out to the oppositely charged electrodes. Ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solvents present in the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too larger size. However, the pores of filter paper can be reduced in size by impregnating with colloid ion to stop the flow of colloidal particles. The usual colloid ion is a 4% solution of nitrocellulose in a mixture of alcohol and ether. An ultra-filter paper may be prepared by soaking the filter paper in a colloid ion solution, handling by formaldehyde and then finally drying it. Thus, by using ultra-filter paper, the colloidal particles are separated from the rest of the materials. Ultrafiltration is a slow process. To speed up this process, pressure or suction is applied and the colloidal particles left on the ultrafilter paper are then stirred with fresh dispersion medium, that is the solvent, to get a pure colloid. Let us revise whatever you have learned in this module. Colloidal solutions are intermediate between true solutions and suspension. The size of the colloidal particles range from 1 to 1000 nanometer. A colloidal system consists of two phases, the dispersed phase and the dispersion medium. Colloidal systems are classified in three ways, depending upon number 1, physical states of the dispersed phase and dispersion medium. Number 2, nature of interaction between the dispersed phase and dispersion medium. And number 3, nature of particles of dispersed phase. Lyophilic, lyophobic, multimolecular, macromolecular and associated colloids are various important colloids. Lyophilic colloids, owing to strong affinity between the particles of dispersed phase and the dispersion medium, are formed by merely mixing and shaking the dispersed phase and dispersion medium together. Lyophobic colloids are prepared by condensation and dispersion methods. Briggs arc and peptization methods are the important dispersion methods. Dialysis, electrodialysis and ultrafiltration are the methods used for purification of colloids. In the next module, we are going to discuss about various mechanical and electrical properties of colloids such as Brownian movement, Tyndall effect, etc. Thank you.